Optical technologies go back a long way in Hanover. Hanover Laser Center was founded in 1986. Over the past 20 years, pioneering work has been carried out, especially in thin film, space and laser technologies, and these are cornerstones of our work in Quest.
In the research area D,
In Quest's Research Area D, Enabling Technologies, we've concentrated the technology areas of Quest that are there to stimulate and support science in the other areas. These include nanotechnologies, which are later used for storing cold atoms and molecules, laser technologies, which are used for future gravitational wave detectors or for optical clocks, fiber technologies, which play an important role in all areas, and, of course, space technologies, which are going to make it possible one day to conduct certain experiments in space. So, for example, in the group ultra-high quality optical layers and characterization, new optical materials and thin film processes for laser components are being developed. In the section Laser Components, we're trying to optimize optimal coating processes and to produce ultra-high quality optical layers. And under the auspices of the Excellence Initiative, we're trying to improve these well-established coating processes and to produce fewer losses. And with this, less diffusion, less absorption, and the highest possible reflectivity. Everyday mirrors don't reflect enough light to be used in lasers. Simple laser mirrors often used to be made of polished metal, usually copper or aluminium, or they were made of glass and coated with gold or silver. Such mirrors have major disadvantages. Part of the laser light penetrates the metal and is absorbed there. In addition, the mirrors do not let any laser light through. But our aim is to reflect the laser beam with virtually no loss and to use it outside the system. For this, we make multi-layered mirrors. These consist of two transparent materials with different refractive indices. By stacking the different materials, we get a series of boundary layers. And these have an interesting effect. The interleaving produces a high reflectance value. Such mirrors are called dielectric multi-layer mirrors. If we took an everyday shaving mirror and introduced light there and put two light mirrors next to each other and kept reflecting the light back and forth, we'd have, after about 100 round trips, well, the light beam would no longer be visible. That's absolutely useless for a laser. We need a significantly higher reflectivity so that the beam can travel back and forth 1,000,000 times between two mirrors. And now we want to increase this reflectivity to 100 million times, because only with these high-quality mirrors is it possible to run the modern optical clocks we want to use in Quest. So outstanding mirrors are absolutely essential for building a stable optical clock. But these mirrors are only one essential element in an optical clock. Other research areas within Quest are responsible for other equally essential components.
in Area D,
we're working on the sub-Hertz laser. That's a laser with a very narrow line width, so it can measure atomic transitions with extremely high precision. This is of great relevance for optical clocks, which will one day replace the atomic clocks we know today, in order to bring even higher precision into the various experiments. An essential basis for this sub-Hertz laser is a resonator that is produced using a special coating and construction technology, and we're working on this resonator above all in Area D. Laser technology is also becoming more and more widespread in space. Laser opens up possibilities that we didn't dare to dream of in the past. But in space, laser systems also have to meet particular challenges. We have to consider, for instance, what effects the vacuum has on the optical systems, how gamma radiation harms the system, and much more besides.
In Quest befassen wir uns mit Technologien, die dafür benötigt werden,
In Quest, we're concerned with technologies that are needed to send laser or other optical systems into space. These technologies have to take not only the primary, i.e. optical properties of such a system into account, but above all the mechanical or thermal properties. Here, for example, we are developing laser oscillators that have to be very small and compact, while at the same time being able to cope with the rough environmental conditions of space. So they have to be mechanically stable enough to stand the high vibrations, shocks, and also the very great ranges in temperature that can occur here. We test such systems, for example, in thermal vacuum chambers, a chamber like the one you can see here in the background, where we can put these systems into a vacuum and then test them at very wide temperature ranges, as in this case from -70 to +170 degrees.
Von -70 Grad bis +150 Grad testen können.
Together with NASA, the European World Space Agency ESA is planning an expedition to Mars in 2018 on board the Mars rover. And this will contain technology from Hanover's Laser Center that members of Quest have helped to develop. So laser will be used to look for traces of organic material on Mars.